Okay, so today it will be much less constructed than the other day because it's a lot of open questions and some small results that are not completely mathematically sound that I want to explain to you so that you might be interested in having something more formal about those questions. For the people who were there yesterday for the exercise, if you remember, we ended up here and I explained what it is. So we treated the real data of the rat in the maze. And you remember the rat in the maze was, so here is typically when he's doing this path, that's what I called comp 1. And either he's doing this path, which is comp 2. Okay? And you can reconstruct on the neuronal data the Hawkes network that goes with this data. And you see that you reconstruct something like this. And so the blue means you don't, the Hawkes estimator is saying there is not even a spontaneous part. So blue means your neuron is almost silent, right? Ha. Yeah. Red means you have a spontaneous activity, whatever it is. And for instance, you see that this one is firing in this behavior and this one is not firing in this behavior. So this would be typically what you had. This one is coding, firing rate coding for this behavior, right? Blue, so a bubble is a neuron. This is the graph of interaction. You put an arrow when the Hawkes estimate. Okay. Blue means the spontaneous part is 0. So if you have no edges and it's 0, it means your neuron is silent or almost silent because as you know, the lasso will truncate everything below the noise level, so it might have some spikes, but it prefers to say it's 0 instead of making a mistake. So when you see red here and blue here, yeah, it prefers that. So it's as I said you for the thresholding estimator, at one point, if there are very few spikes, your estimation of the number of spikes might be super noisy. So it prefers to say 0 than to say something which is garbage. No, 0 means it's too small to be well estimated. So of course, if you have red here and blue here and no edges, it means that the firing rate here is really positive, whereas here it's almost 0. So there is a difference of firing rate between this condition and this condition for this neuron. Yes? So if you remember the beginning of the course, it means that this neuron is firing rate coding between this condition and this condition. Okay? But you can also look at those 3 neurons here, and here you see, we will zoom after that, but the network that you reconstruct for those 3 neurons is different from this behavior to this behavior. Okay? So let's zoom here. Here you have a very small edges that you don't even see. You see that the pattern of interaction is different between this one and this one. Okay, so it's firing, it's network coding, if you want. Yes. Like why this one is red here and blue here?
No, the other ones.
Those ones?
No, the 3 ones.
Yeah. Those 3?
Yes, they are firing both functions.
Yeah. So I don't know if they have, you have to look if they have a different firing rate or if they are the same. Maybe they are firing rate coding, maybe not. It's just that with this representation you cannot see. Yeah. But you can have a look. That was just that this one, it was obvious. And this one as well, that they are firing rate coding because it's 0 and something else. Oh, okay, sorry. So, okay. I just want you to show, because yesterday I didn't plot them, what were the size of the interaction function. So the size of this interaction function, I don't know if you see, here is typically 20 Hertz, 10 Hertz. Sometimes it can be like here about 2 Hertz, but most of the time it's quite big.
H.
It's a H, yes.
So it's a product of the snap H plus and the
Hg to I as a function of t. If you want me, because it's super small, it's here you have 20 hertz. It's in hertz, right? H. Because it's what you had to the firing rate when you have a spike, so this is in hertz. Okay?
and then becomes small.
Yeah, at one point it will become small. Here I made a very rough, it was with yesterday parameter, I can make it with more bins. Here, on a very short range, it's super big. For instance, it's the kick that Mauro wanted to see yesterday. Really close to zero, 10 milliseconds here, you have a kick of 20 hertz when this one is firing. Okay? It's just to give you an order of magnitude.
And the fact that it's
It's because I forced the estimation to be piecewise constant. But if I put more bins, it will be more clean. That's the parameters of yesterday simulation, because I wanted you to see the order of magnitude. It will be important for my questions after that. Okay. So now let's go back here. Yeah. So here it's another vision of, it's for another rat at another time. For this session, you had 4 paths that were there long enough to have a good estimation of the network. Here, it's a slightly different condition. It becomes redder if the interaction function is stronger. Before, it was just the width of the row that was that. But for instance, you see that clearly this path or this path and this one have nothing to do as a network. Okay?
the one in the middle.
So this one is for this path. This one is for the straight path. And you see that the graph for this thing and the graph for this thing are completely different. Yes? Also, you can see that if you look at the firing rates without putting the spontaneous activity, here you have the firing rates. Okay, the pattern of firing rate is a bit different from this one, but like the 2 ones that are firing the most are also the 2 ones that are firing the most here. Yeah. Okay, so the question is now, can we do network coding? Meaning I want to compare what I can decode by just looking at firing rates with what I can decode when I look at the graph. Okay? So what I'm going to do is this thing. So, say for instance, you have just 2 paths. Say that the rat during one session is doing 100 times this thing and 100 times this thing. Okay? What I'm doing is that I'm taking, for instance, 60, well, it's 2/3 of the path, so that I estimate my connectivity graph from which corresponds to this behavior. Same thing here. I take 60 paths, and I have maybe a different graph. Okay? And then it remains to me 40 plus 40 unlabeled paths. And for each of them, so just one path, so it's just few seconds of spikes. I want to guess if I'm more doing this thing or more doing this thing. And so what I can do is that for each path, for each of the 80 paths that remain, I can compute -2 the integral of lambda 1. Say this one, the intensity that is described by this graph is lambda 1, and the intensity that is described by this graph is lambda 2. So I can compute this thing on just one path. Okay? No, there is no square here. I forgot a t. I forgot a t. And what did I forget at the same time? So this is my intensity for neuron I that I compare to neuron I. Okay? And then, of course, I sum over all I. Okay? So this is how close the points that I have observed on this path are close to the model which corresponds to this intensity, right?
The graph you picture, sir.
This?
Yes, exactly the one which had one path.
Yeah, exactly. So I have 40 of those paths, right? I'm taking 60 to estimate, and the other ones that I haven't used, I glue them here, and I'm saying that they are the unlabeled path now. And I want to play the game. Can I guess which path the rat is making by just looking at the neuronal data? Okay? So during this path, neurons are going to spike. Okay? One path is about, I don't know, 6 seconds. Okay? So if I am at 10 hertz, I have like 60 spikes. And that's it. I just have 60 spikes. And with these 60 spikes that have appeared during this path, I can compute that because here I have my spikes. And I can compute, therefore, how close, because this is my least square contrast, if you remember yesterday. I'm computing how close my spikes are from the model described by this graph. Yes? I do the same thing with lambda 2. And the one which is the minimum will be my guessed label. Okay? Exactly. So lambda 1 corresponds to this graph that I have estimated with 60 of the path, and lambda 2 corresponds to this path. Okay? So with that, if there is a code, I mean a network code, logically, I could be able to guess which of the path the rat is making by looking at the minimal criteria. Okay? So I have I hat, which is, so this thing is my criteria under 1, under 2, etc. for the ith condition, and I'm saying, okay, I want the arc minimum of my least square criteria over all I in the condition. Okay? Okay. So what? Yes. Yeah, I forgot the square. Sorry. And here I forgot dt. It's my least square contrast. My fault. So it's really the least square contrast we have seen yesterday. Yes? You're with me? You can do that with a graph, or you can do that with estimating the firing rate like it was a Poisson process for each of the process, and look at just the firing rate which is the closest. Okay? So you can do this thing with a Hawkes model or with a Poisson model. And so what I'm giving you is the difference of good guess in the proportion between here Poisson and random guess, meaning I'm just playing with dice over the path. And if there are 4 paths, I have a chance 1 over 4 to be in a given path. And you see that Poisson and random, it's almost the same. Poisson and random are almost the same. The difference is 0, because with 60 spike, you have too much variability to correctly estimate the firing rate. So even if your neurons were firing rate coding, you have not enough information in just one path to correctly guess it. Whereas if you make the difference between Hawkes and random or Hawkes and Poisson, they are all, of course, almost the same, you are much higher, like by 10 to 20% higher than what you can do with just Poisson.
What do you mean?
Oh, it means that random guess can be sometimes better than Hawkes. I mean, this is a box plot, right? So it's in average. Sometimes your random guess can be better, but it's of course not what will happen all the time. You see what I mean? It's just that maybe if I take at random a guess, and if I'm taking the I hat that is there, sometimes I hat is worse than my random guess, because my random guess, by chance, can be very good. Okay. But of course, it's negative, but the average is above 0. Yes? What?
So what's the percentage effect of the Hawkes?
You will see it later. Because after that, you have to distinguish a lot of stuff. In particular, of course, here I'm making just a difference, but the guess is better if you have less path in competition. The guess is better if you have more neuron. The guess is better if you have more firing rate. So because of all that, it's a bit difficult to just plot it like that. And it depends also on the stage of learning. So the good representation will be in the next slide. But I just wanted to point you something out for statistician. It's a bit amazing what's going on here, because when you are looking at firing rate neurons, meaning just Poisson, if you have 10 neurons, you have 10 parameters, and that's it. When you are going to Hox process with 10 neurons, you have 100 parameters, if I'm just having one parameter per interaction function. So it means, usually, when you increase that much the number of parameters, usually you are overfitting, which means that when I'm doing my cross-validation estimation of what is my guess, I should be very bad when I have this huge number of parameters with respect to a very small number of parameters. If I don't see that, it means that those 100 parameters that I want to estimate, which correspond to the interaction between the spikes, between two neurons, they are fundamental for the coding of the network, okay? So in this sense, the coding of the network is much more powerful than just firing rate coding. Okay, so now the graph that you wanted to see. So you see that's the stage of learning. This is when the network is in DMS. This is when it is in DLS. Remember, there were two regions we were recording. Here I glued together everything, but in fact, the p-value that I told you is, I took this random variable, which is my proportion of good guess, and I bet a beta regression to find what are the explanatory variables. And among the explanatory variables, I can put the region, but I can also put the number of neurons. So here is the region, the number of neurons, the number of paths, the firing rate, and of course the cross effects. And the p-value adjusted for its multiplicity is super strong, of course, for the number of neurons, because the more neurons you have, the better is the guess. For the number of paths in the same way, because if you have a lot of paths, the problem is much more difficult to do. For the firing rate, again, if you fire more, it's easier to do. But those are just like classical explanatory variables that have nothing to do with biology. Here you have something that has those to do with biology. DMS is much more coding than DLS, meaning the network in DMS is really doing something as a network which is more powerful than the DLS. Yeah, it's a blue one. Here you have the box plots of all the guess. I put together because you have too many variables. So here it's very large because I put together all the variables. But of course, the analysis for the difference, I made it by putting all the explanatory variables. So you see DLS is below DMS. What is also funny, because you can compare stages, is that both of them are increasing with time. You see that DMS might be more slowly increasing than DLS, but that's it. DMS as well is increasing. Okay, yes?
Maybe I missed it, but the power is the frequency
of good guess. Sorry, I forgot to say. It's the frequency of good guess. It's the number of time this I hat is equal to the true I that's of the path. So the number of times, the percentage of time I'm able to good guess the behavior of the rat.
So just by chance?
By chance, it depends. It will be 1 over the number of paths. So that's why when I'm gluing it all together, it's a bit weird. It depends on the number of paths. And what is weird, which is hidden here, is that, of course, when you learn, you have less and less paths that the rat is making. But the fact that it's increasing is even when I take into account this explanatory variable, which is the number of paths. So the fact that it's increasing, it's for fixed number of paths. You see here that it's globally increasing, but you might think it's because the number of paths just decreased. In fact, it's really another effect. Okay. So I remember you, DMS, the red one, is involved in goal-directed learning, so should be involved, at least at what they thought, at the beginning of the learning. Dorsolateral striatum was involved in habits, so it should be involved at the end of learning. And you see that even at the end of learning, DMS is still more powerful than DLS, which is not what they were expecting. Okay. So, first of all, do we have a contradiction? I mean, from biologists. A contradiction because we have seen in the first day that the number of firing rate coding neuron was decreasing for DMS. Is the red one. So, for the goal directed, so it should be involved at the beginning and then decrease. Okay? And that was what we were seeing on the firing rate. But if you look at it as a strength of the network, DMS is still there at the end. So it's not decreasing for the network, whereas it's decreasing as a firing rate. Which means that the important part of the code that is staying until the end of the learning is not something which makes one neuron fire much more than another one. It's the synchronization effect between the two neurons. And this thing stays much longer time in the region than the difference in firing rate. And that's also why Hawks is more powerful than Poisson to predict the behavior. It's because it looks at this pattern of interaction between spikes. And that's why even with more parameters, it's able to much more classify everything, because this interaction that is important until the end of learning. Okay? One of the interpretations that we could have is that, of course, the brain would like to keep as much stuff in memory to avoid having to redo everything all the time. And in fact, firing is very energy consuming, whereas keeping the network in a kind of synchronized way should consume less energy. That's also why people were thinking that synchronization was part of the neural code. So one possibility for having this network coding that stays until the end and firing rate coding that is decreasing is that it might be easier for the structure to keep this dependency in time with less energy, so that if he has to reuse it again for learning another path, another rule than what is becoming an habit in the DLS, then he can reuse the connectivity to make it learn quicker. I think that's my very naive interpretation as a mathematician. There are a lot of stuff that we need to check from a biological point of view to see if this is really what's going on. Yeah, sorry, it's the percentage of time I hat is equal to the truth. Yeah, the right guess. So that's what I call the encoding power. Yeah, but it was not expected that it would stay in DMS. DMS, it's there for goal-directed behavior, which means that if you are into an habit pattern, you can remove this place of your brain, and you still know how to do that. So the memory that makes you have this behavior, you don't use DMS anymore. You use DLS. Because if you remove DLS, then you don't have habits. But of course, they were making it was very harsh for them to decide which part of the brain is doing what, because they were removing complete part of the brain. So you need DLS for the habit, okay, but there is still a trace in the goal-directed part of your brain of what you have learned. And this stays a long time. Maybe it will die out later, much later. But at least it will stay longer as a network than as a firing rate code, because it consumes less energy. At least that's what I think.
The second claim refers to DMS.
Yeah.
And what do you look at DLS about the strength of
So the strength of coding of DLS increase in firing rate and increase in network. So they are aligned, and they are aligned with what the biological theory would say, which is DLS should be there during the habit, which is stage 4, because if you remove DLS, you cannot have habit. So the code of what you are doing should be in DLS somehow. Yeah?
You found the bigger interpretation of is just to name.
Yeah, and what is the message that is important is that DMS is there also at the end. And there were other papers with other variation and other tasks that were seeing kind of the same stuff that was like the role of DMS might be more important than what people think. Okay. But it's not just a biological question, it's also a mathematical question. Because if you look, yeah.
When you say network, do you mean that, for example, if you calculate the joint distribution, all the factors will be the same?
Yeah, and I will come to that. But yes, in fact, it's order 2. It's a covariance that is important, and not just the firing rate. So if you look again just at here, sometimes you reach 90%. Okay, it depends on the number of neurons in your network, the firing rate, etc., etc. But there are some experiments where we reach a correct guess of 90%.
So this box plot was made looking at different hats or
Yeah.
different hats. So you have a very clever hat which succeeded.
No, it has nothing to do with how good they are. The stage has to do with how good they are, and stage 4, they are all super good. That's not a problem of rats. Even, I mean, it's a problem of region. Here, in stage 4, all rats, they achieve, I think, 90% of reward. 90, yeah. So they are all pretty good, and they are making loops like that super fast in the maze because they get reward at each point. So it's not a performance problem. I mean, in this stage, you can discuss a little bit before, but in this stage, they are all super good. It has all turned into an habit because we are like 20 days past the beginning of the learning. So they know when they arrive in the maze, and they are underfed, so they really want to get food, and they are just making loops like that all the time.
How do you interpret one is have a 0.9 and 0.4?
This thing?
Yes.
It's because just I didn't got good neurons. It depends on where is my, well, for the neurons, they are recording the electrodes are recording the neurons that are nearby. So depending on where I am, I'm not that good at, because I didn't get enough part of the network of coding neuron. Also, it might be because I'm in stage 4 sometimes, and it happens more and more when I arrive over there, I'm losing neurons through the experiment. So usually in stage, for some rats in stage 4, I have only 1 neuron. And by using the auto interaction function, you still have information which is better than firing rate. But still with 1 neuron, of course, you cannot be as good as if you have 10 neurons, right? I mean.
You are losing due to cicatrization.
Yeah. They are moving the electrode, but still at one point, at the end, here you have some rats who have been in the maze for 50 days. So it's really a lot. Okay. So from a mathematical point of view, if you think about it, you have put your electrodes inside the 3 atom. Probably you haven't recorded connected neuron, which means that you have a network, an underlying network, which is like that. And what you recorded are those 3 neurons. And what you reconstruct out of 3 neurons is an edge like that with Hawk's processes. You see that they seem connected. And the question is, so at the end, I have like 10 neurons out of a soup of 10,000 neurons. I'm able with just 10 neurons and the pattern of interaction. And you have seen at the beginning, that's why I showed you, it's not like the 10 neurons are connected. It's like 2 or 3 of them are connected. And with that, you can guess the behavior of the rat. And so the question is, what does it mean for the network that you can do that? So that's what I wanted to check, and that's where I will start some small computation. So what I'm going to do is, okay, this is my neuron, this is my spike, and I'm going to bin, okay. What? Red? Okay. Yeah, I should remove some of them. So what I'm saying, I have my spike trains. This is a bin of size delta. When you have a spike in it, you put a 1, 1, 1. Here you put 0, 1, 0. Okay. So that's the discrete stuff that Eva told us about. What I just want to point you out is that if you compute the so this is my xi of t. Okay. If I compute xi of t, you get a certain probability pi, right? But in fact, this pi, if you think about it in terms of firing rate, just to get an order of magnitude, this has to be think like mi times delta, where mi is the firing rate in hertz. Okay. Mi will be fixed because my neurons are not going to, their firing rate is like 10 hertz, and whatever I do, it will be 10 hertz. But delta can go to 0 if I want in this framework. Okay. Next thing, I'm going to look at what's going on for two guys. So xgt. So I want to look at the quantity xit, xg, t plus h. Okay? Minus eventually this thing for the covariance, right? So this is what I will call vijh. Okay, there are two cases. The first case is when I equal j and h is equal to 0. Yes. Yeah, sorry. Yeah. Again, new article, so problems with notation. Yes. Yeah, and by the way, there will be two h. So yeah. When there will be a h with an indices, which will be my interaction function, a h without indices, which is my number of bins. Is it okay? Okay. Okay, so if you think about it, it means that vii0, it's what is the expectation of xi minus the expectation of xi to the square. So in order of magnitude, this thing, it will be in delta square, whereas this thing will be in delta, right? So the first order of magnitude when delta tends to 0 is that this thing is of order mi delta. For the other ones, it's less clear, and the assumption we are going to make is that when h is positive or when I is different from j, this thing is in delta square. This is an assumption. It's just that this is the assumption that will avoid that two different neurons, can have spikes at almost the same time. So when I'm going to let delta tends to infinity, the spike trains that I recover are simple point processes where two neurons cannot spike at the same time, okay, or cannot spike, and they are all continuous with respect to the Poisson measure behind, so there is no fixed delay between them and stuff like that. If you want the other assumption, like this is still of order delta because you want to model synchronization, there is another paper by Cass, I don't remember the other name, and Low, I think it was like that, which is describing another setup where this is of order delta and what is a good construction of two-point process that really synchronize at fixed distance, okay? But we are going to do like this because we want to be in the case where in the limit we could be Hawkes processes in continuous time where they are all absolutely continuous with respect to the Poisson measure behind. Okay, so that's what I'm going to assume from now on. So that's what I'm saying here. Yeah, so that's what I told you, exactly. And now I'm going to say, okay, so in this setup, what did I do so far? I tried to approximate my, not pi, but I tried to approximate the expectation of xit given the past. And I approximated it, but it's an approximation, okay? It's like I tried something, and maybe this is not the good model that is behind. What I tried as a model when I'm making my reconstruction is a Hawkes model. So the Hawkes model, it's okay, it's mu I plus the sum over I in F. F is my set of observed neurons. And then I have an interaction function. So, okay? When I write it like that, this is a probability. Remember Eva's course, you can also interpret them as like weights of the Calico decomposition, which means that mu I and j, they are numbers that would look like probabilities. If we want to have the good limit, you have to think that those mu I, they are going to be of order delta when delta tends to 0, because of course you want to end up in the limit to the Poisson, to the Hawkes process typically. And same thing for j. Yeah. Oh, here, yes, sorry. Sorry. What?
Why don't you trust what we wrote in
Because I want you to write this thing down. As you want. Okay, I can go like that. Okay. What? J is here. Yeah.
I fix sum over j.
Yes. Okay. You are right, not trusting the flags.
You see? Ha!
Yeah.
Yeah. Okay. No, but just let me write this because I really need it for the sequel. So this is going to be my function that you have seen before, which is like 20 Hertz times delta. For the same reason, okay? If you wanted to go to the limit and have the Hawkes process in the limit, you need something like that. And you have seen on real data, this thing is 20 Hertz. So if I change my delta, this should shrink to 0. Okay, and now we are in an ID case. In fact, what I did was minimizing the least square criteria. And so the least square criteria, if I was observing like an infinite sequence, would be just minimizing this thing, right? And of course, if xi is really a Hawkes process with this kind of formula, when I'm minimizing this stuff, I should get the parameters mu and j that are the ones giving me my intensity. But if xi is not following this model, well, my solution is just the mu j's that are minimizing that. Okay. So what we proved, and it's very easy, it's just that you derive your least square criteria and you find where is the optimum. And you find out that VGI-U, yeah, U, it's better, U is what? Is the sum over all the neurons that you have observed, the sum over all the lags, and then you have to go from J to K with your covariance matrix, and like the last step is your interaction function. Okay, so it's a convolution where the last step is the interaction function. And in fact, the J that are the solution of the minimization problem, which is also the interaction functions that are the best to mimic what you see on your data, are the ones that satisfy this equation. So the covariance with lag U is equal to the convolution products between the covariance at lag U minus S and the interaction function. And if you can solve that, you have your J. Which means the J are not anything but another view on the covariance matrix. It's just that it untravels somehow when you have 1 which impacts 2 and 2 impacts 3. Well, if your correlation between 1 and 3 is sufficiently explained by an arrow from 1 to 2 and an arrow from 2 to 3, that will be 2 will be this neuron in between, then you don't need to put an extra arrow from 1 to 3. It's good. This is sufficient to explain the covariance that you have seen. Once you have those interaction function, then what is mu bar? It's just the spikes, the spiking rates of your observed neurons that you cannot explain with just the interaction function of the other. Okay, so if you can explain the firing rates that you have with what comes from the other one, then mu becomes 0. If you have more spikes than what comes from the other side, then you need a spontaneous part to compensate it. And if you have fewer spikes than what was expected, it means that your mu can be negative. Okay? And in fact, there is no constraint on the least square criteria, so the G might be negative, the mu might be negative. This formula cannot even be a probability. I don't care. What is important is that it is the closest to xi as a least square. And as long as this is holds, then this is, in expectation, the best you can do. So this is how you would approximate any kind of model that is not necessarily a Hawkes process by a Hawkes process on your observed neurons. Okay, so this is what I said, the interpretation. And now, if you look at the formula, and say your G bar are bounded by R, okay? And of course, I showed you the thing before. G is equal to H times delta. H is 20 Hertz. So of course, G is bounded. Okay, if you look at that, you see that your covariance at lag U is mainly, this is of order delta, right? So this is mainly your interactions that you are reconstructed. And then what you have left is something that is in delta super small if the size of your observed network is small. My size of the observed network is like 14 neurons, so it's super small. R is small, okay? And I put a memory for my J that is super small, and this is what I did because I put 100 milliseconds. So what I'm reconstructing on real data is in fact only, at first order, the covariance. And that's it. I mean, it's a very complicated formula, but in fact, what I'm reconstructing at first order is just this covariance, okay? That's also why Shinomoto, for instance, and Mauro and you can look only at covariance to explain everything and don't need to look at everything and Hawkes and Lasso, etc., because at first order, it's what you have. And I think it's also what is hidden behind what you did to detect what's going on between I and J. It's almost the same kind of intuition. Okay, so now let's assume that G is equal to H times delta, and you assume that this is bounded. What it means if you reverse the equation is that your interaction function, which is H times delta, this is Mj. So now I pass delta on the other side. This is what? This is just your covariance divided by delta square. And here you have something which tends to 0 with delta. Okay? So as I said, your interaction function is basically your covariance. Okay. And now we can think, what does it mean for the bigger system? So now I'm going to assume that the bigger system is Hawkes. So I'm going to assume that what lies behind is a formula like this, but now this I is much bigger than my 10,000 neurons and not my 14 that I have seen. And I have interaction function like that and spontaneous part. Okay, and again, because I need to have this approximation when delta tends to 0, my phi are of order delta. Same thing for nu I, but I don't care about nu I. And so if you think about it, of course, the best approximation in the big model of your Hawkes process by a Hawkes process, it's itself. Which means that for the big model, the same formula is true. And the covariance between J and I with lag U, here I'm looking at all the relay, but in the big network, and all the relay in time of the covariance between J and K with lag U minus S. And then I go there with my direct physical interaction between K and I at lag S. Okay? This is of order delta square, except if J equal K. If J equal K, then you get, I'm going from J to I, because K equal J, so J to I with lag U. And here is what remains. This is, I have a delta from here, so I have a delta square. I put this, but you can forget. It's just because the firing rate, the covariance of this is in fact this time times this thing. Okay, so this is delta square. So this is my direct interaction. And then I have the sum over the rest. And the sum over the rest is what? So I have really another relay. So K now is different from I. Or could be I, but at a different time. So I'm going from J to K with lag U minus S and this thing. And this is of order delta square. So now this whole thing here is of order delta cube. Okay, so first term of order delta square, second term of order delta cube. Okay, so in fact you have two cases. If, as I showed you on my 14 neurons, I am seeing with my Hawkes reconstruction a big arrow between J and I with height 20 Hertz, then it means that this thing is really macroscopic and that I can see it. So there are two explanations for that. Either J and I are connected, and then the order of magnitude that I get here, which is of order delta square, is also the order of magnitude that I got from there. This is just negligible, and it just means that I have recorded neurons that are physically connected. But if you speak to neuroscientists, they will tell you that first, they are not sure that you are recording, I hope Daniel agrees with me, connected neurons. And there are even experiments like Sonia Grün told us in March, where when you record them, they are so far away that you are pretty sure that they cannot be physically connected. So if you are in this case, what does it mean that you are reconstructing an edge like that? Well, then it means this thing is still of order delta square, but this is 0. So it means that the number of relays and paths that you can make here compensates the fact that this thing is of order delta cube. And so it gives you an idea of how the network can code, and you can decode with only 14 neurons, because there is in fact so many paths in between the two neurons that you have recorded that are having a certain strength, that in the end you are reconstructing something even if those two neurons are very far away. And that this pattern of the network that would change from behavior is that the whole network behind is changing from behavior to behavior macroscopically. Because if it's not that, you cannot have such a big switch in your interaction function between two behaviors. And I have no idea how a network can do that. But it's certainly not mean field. Because mean field, in the end, everything decorrelates, so you shouldn't be able to see that. There is another topological proof, which has nothing to do with probability or statistics, that the network is weird. Well, not a mathematical model. It's a work by Catherine S. In Switzerland, and she's a topologist, okay? And she looked at a cortical barrel, and she looked at many structures that I don't get because I'm not an algebraist. But the one I got was the simplex. So what you want is that to find in your network, you have a starting point, an end point, and you want the graph to be complete, and that, so I think the starting point is there, sorry. So you want a starting point and an end point which should be there, and you want the graph to be complete, and that all the rows are putting mass that are coming from there, and the mass that is coming from there arrives here. So, okay, you have a very structured, like complete network that is going from a source to a well. And she counts this number of structure. And she counts it on biological data, that's the bio one, it's the blue one, and she counted it on random networks. And you see, what is amazing is that on the biological network, the size of those directed simplex, complete simplex, goes at 7. No way that any of those more or less biologically inspired model of networks can reproduce such a huge transfer of information from a source to a well. And this is probably linked to the number of paths I told you. Like there is so many paths that goes from one direction to another that if you are in this network between the source and the well, of course, there are so many paths that are going between two guys that are going from the source to the well that in fact you see somehow the transfer of information between the source to the well without even being recording the source and the well. Yes?
just to say that there is some external field or any, or they are looking at the same stimuli, it could be a simple explanation.
Yeah. But still, this external stuff will drive all the network to do that. Because if you don't have even if you have an external neuron that is bombarding all of them, well, okay. If they are really bombarding all of them, then it could be. Yeah, I agree. Okay. Yeah.
The conclusion was that the network is not random. That is the conclusion of this article.
Not random. Maybe it's random, but we don't have the good model yet to produce network that would have such a huge number of directed edges from one hand of the cortical barrel here to the other hand, if you want. It's like the real network is organized maybe at random, but in such a way that information that goes through it really goes through it in a redundant way and without being lost in the middle because of propagation of chaos or whatever. It really goes through. I think that's what it means. But after that, as I said, I'm not an algebraist, so there are a lot of quantities that they compute, which tends to say that it's in between. So the quantity are mathematical, but they compute it on real data. Have a look. No, but she's good, Catherine S., really. And she's a mathematician.
It's not good, but what they wrote. So you see, it's just this conjecture that everybody more or less accepted that the maximum information is transmitted as a critical point. Well, it's wrong.
No, but she's not saying that.
No,
she's
you
not.
see, everybody accepts this because Perbach said it
Yeah.
once, but it's wrong. So if for concrete examples, you can prove it's not true.
No, but here it's not mathematical delirium. She's just taking those algebraic quantity and computing them on data.
But it shows something you cannot see directly. You try to prove it for a concrete model, at least for the case. We want to prove it was true. It was not true. So it's a problem, this answer, that you don't understand.
Have a look. Have a look. You will see. You will tell me.
I don't think so, because
As you
I
want.
don't succeed in reading this article.
As you want. The only thing that I wanted to say is that the coding property of a network, it's much more complicated than the coding properties of a neuron. And it probably involves much more math than just statistics and probability. And I don't know yet how far and what is new that has to be invented to understand what is the kind of graph that is behind. One of the possibilities would be expander graph, but expander graph are new. Expander graph? Expander graph, it's a graph that when you cut an edge, it's very likely that the information still travels through all the network without any problem, except that expander graph is written in such a way that it's not a directed graph. And most of the computation on expander graph are not for directed graphs. They don't really know how to do it with directed graph.
Responded with the R.
Yeah, it's expander graph. It's a algebraic structure that I don't completely understand, but a lot of people think that probably one way to understand what is behind is to look at those expander graphs, and that they might be a good model.
Let me ask you a question. At the beginning, you said you tried to identify the coding properties using the time rate of the key.
Yes.
And then when you speak about the coding property of a network, what do you mean?
What I did here? Here you have a network, and the network is coding the path.
The graph interaction
Yeah.
between.
Which basically means behind. I taught you that with a graph, but in fact it's the covariance pattern which is sufficient, and so it's a second order property of your spike trains, which would be the code, right?
It could be also the law or stationary law of the system. The
What?
definition of coding property.
Yeah, if you want, but I don't think stationary is the most important stuff in it, because your brain will change from state to state all over the. Yeah, if you want.
Some kind of, because otherwise, even all of this.
At least, if it's in the stationary distribution, you should at least have the covariance. If in the stationary distribution, you are Poisson, it's not sufficient to describe what you see. Maybe you need third-order properties on top of that. For the moment, we know that we need at least second-order property. People like Sonia is trying to look at further order properties. But then it becomes computationally crazy. But Sonia Grün. Yeah. Okay, and so if you want, it would be super nice to have somehow the same theory we had for firing rate coding neurons to understand what it means that it's firing rate coding from the brain perspective for the network. But this, for the moment, we don't know how to do. So we know how to detect coding network as we have detected coding neurons, but then the theory of what the brain is doing with that, we don't know. Those are the references. And then now I want to switch to something that might be of interest, which is a bit different. Because one way to approach that is to say, of course, the network is particular because the network has learned. If the network didn't learn anything, probably it would be a random mess. And we have such a pattern because the network has learned. Okay, has learned during even embryo development, and then when you were alive, etc., etc. So it means that if you grow neurons in culture, probably it's a complete mess. For the embryo, it has already a kind of structure and pattern that is making this better. And then the child is learning, and then your whole network, days after days, is becoming sparser, and so more with more directionality in it. And so we wanted to look a bit at those learning data, but learning is a mess from a statistical point of view. So I want to tell you where we are in this learning data framework, but we are not very far, okay? So don't expect too much. We are just at the beginning. So it has been a work with a lot of people, and I just want to point out that this all began with an interaction, not with neuroscientists, but with a psychologist in Nice, Fabien Maty, and with whom I directed Giulia Mesadri, who was a pure mathematician and wanted to learn psychology. And she did an amazing job at understanding enough psychology to put math model on it and say something interesting on that. And of course, there are all the other ones. You recognize Sophie. That's her advisor with me. I have, in fact, 2 PhD students right now on the project from the math point of view. And of course, you have also the biologists, computer scientists, and so on. Okay, so the problem is that learning behavior is already complicated even without speaking of neurons. So you are going to imagine you are a kid that he tries to learn to go to school, okay? And so, in fact, you are using strategy even if you don't think about it when you are learning something. And there are several strategies you can think of. The first thing is similarity thinking, which means, okay, I need to pick a shirt to go to school. I remember that I was happy in a kind of pink shirt before, so I'm going to go for the pink shirt again, okay? So I learned that something that is close to what I liked before should be good in the future, right? But sometimes you cannot do that. Sometimes if you just reason by similarity, you are going to be in big troubles because, for instance, you have to learn that whatever the condition, you have to stop at the red light. And it means that here you cannot think with similarity, you have to think with something else, which is, there is a rule, whatever happens at the red light, I stop. Okay, there are other things you can look, try to understand how you learn that. You want to learn the path to go to school. And so, of course, you can be very slow learner and you can think, okay, so I'm going to learn to go to this crossroad. And then I arrive there and think, and then I go to learn to this crossroad. And then I arrive here and finally I go to school. Or you can think, okay, my mother told me how to go to the market, so this I know. So I'm going this very complicated path just in one run, without thinking. And then I arrive to the market, and then I go to school. Okay? So that's different strategies that you can think of when you are learning in everyday life. And the problem is that now, from a statistical point of view, you want to see the behavior of the individual and guess what the strategy he has done. And if you think about it, well, the problem is that first, the strategy depends on the individual. So no way I can ask all of you to learn something and you will all use the same strategy. So you cannot agglomerate data by just pulling together a lot of people. Next, you cannot ask someone to repeat learning, because once a kid has learned to go to school, well, it will learn to go to school, it's done. I mean, you cannot repeat that. So it means that if you want to estimate strategy, you have to do statistics for non-stationary data without repetition. So from a statistical point of view, it's complicated. What?
You become Bayesian.
No. No, not me. Yeah. So that time that yesterday, Sponskowski told you about regret and learning stuff. I don't know if you remember. So for the moment, I'm looking at a very, very simple algorithm, which is a bandit algorithm. So you can think about it. This is just to make a joke because, well, it's a very well-known joke in cognitive science. You have rats that are pushing a lever, and the rat is thinking it's a rather interesting phenomenon. Every time I press this lever, that postgraduate students breathe a sigh of relief. Okay, and in fact, those boxes really exist. They are called Skinner boxes, and the rat has to learn to press lever to get food. Okay, so it's a very simple learning stuff where he has to understand which lever it has to press to get food. And so what you are saying, one of the most classic algorithm to do that in machine would be what's called an X3 algorithm, which is done as follows. So here are the losses that you will get when you press the lever number k, and it's ordered from 1 to k. And at each run, you are going, well, first to choose the levers that you are going to take with a certain probability. You start with uniform probability. And then you are saying, okay, so this I need to write. You're going to say, okay, so my cumulative loss at time t plus 1 is for lever I, is my cumulative loss at time t. And then what I do is I take my loss for I divide by the probability it, and then indicator that the action that I pick is I. Okay? Why do I do that? Is because in expectation, this thing, because this thing is picked with probability pi of t, this thing in expectation is just pi. Okay? In the original algorithm, and then the last thing is that it's a softmax, so it just means that the probability pi t plus 1 is exponential minus eta li t plus 1 divided by the sum of those stuff. Okay? Okay.
I don't know. No.
Well, not for the rat. Not for the rat. The rat, the learner does not know that. It will rapidly know which one is what because it has to try only a few of them. But still, okay. It seems very complicated to do that because if pi was fixed in time, you would just press one time each lever, you will get the reward, and then you would know which one is a good one, and you will stick to this one for all time. In fact, those algorithms, they are known to be good in adversarial context. And in adversarial context, this is what happened yesterday with Sponskowski. Pi, in fact, can depend on t, and the environment can fight against you to trick you to find something which is not a good strategy. In particular, if you just try once all of them and stick to one, if you change your rewards at one point, you will not get the best thing you can think of, right? So in fact, people have proved that if you have a reward that depends on time, those kind of adversarial bandit algorithm, they are somehow the best strategy you can have, which means you have sublinear, what's called regrets. Sponskowski told you about regret. I don't really need it in this talk, so I will not explain again what it is, but they have very good properties. So most of the algorithms that have been done by psychologists and people in cognitive neuroscience, they look like that because they are there to fight against a changing environment. Okay, so they are slow learners with respect to the optimal strategy that you can think if the losses were fixed. But if at least they are robust with respect to a changing environment. But now we are in the situation where we are making the experiment, the rat is using its very robust algorithm, and you want to estimate here the parameter eta, which is the learning rate. Okay, so it's really nice. That's the only thing that you want to say is that. Okay. What we have shown is something weird, but that was seen on a lot of other models, but we didn't know how to prove mathematically that that was what's going on. We have proved that, so the intuition is there. This is my likelihood, or my log likelihood. And if my parameter eta is fixed, is big, then this log likelihood is super flat. It's so flat that, in fact, you have parameters that are very far away, and mathematically we have been forced to prove it with this rate, but we think when you do the proof that the good rate is this log star, and I will explain what is log star just after. You have parameter eta and delta that are separated by a very slow rate, and the Kullback-Leibler distance between those two distributions is smaller than some fixed delta. And if you think about it from a statistical point of view, this equation, you can think it's the same thing I use with firing rate coding when I minimize the probability of error of test between the two distributions. When you have a Kullback-Leibler that is bounded like that, it means that with probability at least a function of delta, so say 5%, and it's fixed, even if n is super big, I'm going to confuse the distribution with parameter eta and delta. So whatever the estimator, not only the maximum likelihood, no one can make the difference because from a statistical point of view, you have a change which depends on delta that one looks exactly like the other. Okay? So we think the good rate is log n star, and I just want to, log n star is what? This is log of log of log, and you do that n times of n. Okay, it's increasing. But if you take n equal 10 to the power 26, log star of n, is 6. Meaning that, at least from a computer point of view, no way you can estimate eta, because you cannot discriminate with 10 to the power 26 observation two guys that are at distance 1/6. So that's why doing statistics for learning data, you can think it's helpless. Well, not completely, because in fact, you can make eta tend to 0. And we will see what it implies. But if you make eta tends to 0, so typically eta will be eta 0 divided by n to the power alpha, then you can prove by truncating the likelihood that there is a way that first you can predict the probability and the error will tend to 0 with a rate which depends on alpha, but also that like estimating the constant on top is consistent with a certain rate also which depends on alpha. But what does it mean? It means that if you want to estimate something, you need to have a slow learner that is going to make many mistakes. And because it's making mistakes, you are able to guess the parameters that are behind. If it's not doing many mistakes, then you're screwed. Okay? And from that, that's the only real mathematical result that we have. From that, we continued to work with the psychologists. And it also means that if, and they knew it before we arrived, right? I'm telling you the story from the math point of view, but we started with their point of view. They knew already that if you want to understand anything about learning, you need a complex task. Because if the task is too easy, You learn too fast, and you cannot make statistics with that. So they made a very complicated experiment, which is the following one. So you have objects. So you have the small ones, the big ones. You have the red one and the blue ones. You have square and circles, and here you have dashed stuff, and here you have non-dashed stuff. Okay? And in the experiment, you have to learn how to put those objects into category. And the categories they have done is those ones. So like all the black points, sorry, they are in one category, and all the other points are in the other category. So you see the cut is much more complicated than what we get. Like not like all the red are somewhere and all the blue are on some other thing, because this would be too easy, right? So you really have to learn this kind of pattern. So some people will learn it by heart. Some people will try to find a rule. And the rule would be, for instance, like all the, so let me see, that's all the striped ones, except those two, they are more in one category, for instance. That would be a rule, which would help you to start understanding what's going on, and then you will learn exception. Okay?
I propose an alternative. Teach calculus to American students.
What?
Teach calculus to American students.
Yeah, so that's the way you speak, because we needed data, right? And I need this story for later, but because you're speaking about students, Julia, she was giving tutorials in our university. And she said to the students, if you do that, because it was an online experiment, if you do that, you have 0.5 points on your average, right? And she also said them, because that was the loss, so that was the gain. The loss was, be careful, I'm watching you. I know if you would press the same button all the time, so you have really to think. And I will know if you have not think, and if you have not think, it was not true. It was just to make them afraid. If you have not really think about the experiment, you will not get the point. Okay, so the psychology students, they did it, and they did really well. We asked the math department to do it because we were missing data. And some of the math teachers, they said, no, but it's too complicated. I don't want to do that. Like, no reward, no way. Because, in fact, when you do that, and I think Josue and Sophie did it, right? It's about 20 to 30 minutes to get the rule. If you don't know what it is, if nobody explained, of course, before what is this thing. So you present an object, and you say, do you think it's in the black point or a white point? And they say, okay, it's a black. And you say, no, you're wrong, it's white. And then you continue, and you continue, and you continue. So each time you propose a new object. And each time you have a new answer, so you have the feedback. And at one point, you're going to have, you have learned. But it takes a long time, because the rule is very complicated. So you're making a lot of mistakes, which is good for us as statisticians, because we can do stuff with that. Okay, and she put two models in competition. So you will see it looks a bit like this one. It's just that there is an extra layer, which is in the middle. Because now you have a kind of context or state which corresponds to the objects that you are presented. So when you have an object O, the first thing that it does, which is not moving through time, is to activate the second layer of your network. So you have, on the second layer, you have a bunch of activity for each of the nodes. And those nodes, they will have a different signification whether you are what's called alcove or component Q. Alcove, here the second layer are the objects that you remember. And then you are going to activate an object if, well, an object in memory, if the object that you present is very close to them. So that's the similarity thinking, okay? I activate an object in memory if it's close. Here, for component Q, I'm activating feature, like for example, it's striped, or it's red, or etc. But except of that, the mechanism is the same. I have a second layer, and then I'm going to say, let me check that I'm not making a mistake. I'm going to say that the loss of, now I need my object, at time k, and k at time t, sorry, the way I said it before was like this, kt. So k is my category in the end, so for instance, black or white, okay? So this thing is what? Is the sum of your activity. So this is fixed, it just depends on your object. And now you have a synaptic weight, which measure, and which depends on time, which measure how much the second layer I is connected to the category K. And in fact, instead of making this learn, you are making this learn, which means that what's going on at time t plus 1 is going to be what's going on at time t, and then you have a learning rate. Okay, in this thing, it was depending on the strategy, and the indicators and the object belongs to k minus LTK. Don't really think about that. Nobody proved that it converged, but it has been used on simulation, it works. And you see, it's really similar. After that, you do exactly what was there. You do the softmax, etc. So you have, again, this learning parameter eta that you have to guess. And the second thing that you have to guess is, on the second layer, do I put the stimulus that I have in memory and I'm similarity thinking, or do I put rules, like this is red, this is blue, etc. Okay, the other thing that we did is that the experiment, we cut it like that. So we started to put a bunch of time the objects, and you give a feedback. You tell them, no, it's wrong, no, it's true, no, it's wrong, no, it's true. And then you let them do it without feedback. So for 10 objects, you are on your own. And then you start again. And of course, when you are on your own, you stop the learning, because you cannot do that. You don't know if the object is in K or not. So you stop learning. So it means that in the non-feedback period, your distribution is fixed, right? So what you can do is that you use the feedback period to learn eta for each of the two models. And then you use a no feedback period to do cross-validation and try to find which one is the best model between the one that is similarity thinking and the one that is reasoning by rule. Okay? On simulation, it works really well. And we got that, which is already weird. Depending on the order of the presented object, you can force the person to use more the similarity thinking or more the rule thinking. People usually reason by rule on this kind of task, but if you present them in a way that forces the similarity thinking, you can go from most of the people are doing component Q to half and half. And we have statistical evidence that really there is a shift. So we can do that. But there is a problem with this experiment, is that it has been proved psychologically that when you interleave no feedback with feedback, in fact, you're making people even more tired of your experiment, so you're messing up with the learning. Whereas mathematically, somehow you need that because we need it to be in a stationary person. In particular, we cannot do this for animals because if you stop rewarding the animal at one point, it will just stop. So no way this can work. So in simulation, we did something different, and for the moment, we don't even know why it would mathematically work, is that we estimate on the first phase of learning the parameter eta, and then we cross-validate on the second phase of learning. Like we cut the learning in 2 stages, and we try with that, hoping that it wouldn't change the parameter in between, which is another problem. What was super nice for the rat, it's always the rat in the maze. It's always the same experiment. What was nice for the rat is that each day he was forgetting a bit what happened the day before. So we had to put in the model a forgetfulness parameter to model that. But with that, we did the same thing. So you see here, the black is when you change day, and you see most of the time you have a drop in the learning rate, so really forgets a bit each time. And so we put here models in competition, which is for the chunking thing. So the question is in my maze. So remember, the maze is like, like that. The question here, when you start from this feeder here, you know that the good path is that. Where, how does it learn this path? Is he going to here think he has to go there, and here thinks he has to go there, and here think again and has to go there? That would be, I think, at each turn. Does it learn the complete path? Or, and this is what we will show, he thinks here, and here he doesn't think. So that we call the hybrid 3. I will not go into details. It's exactly the same method. What we show by model selection, exactly as we did for that, we have to write down the equation that is there for chunking, but they are of the same flavor. We show that at least the format on which we did it, they were doing that by the model selection. And now you can think, okay, this is all garbage. This is just an artifact of statistics. We went to the neuronal data. And so if really that's what it does, there are two paths that are of interest. You see the red, right? So there are two paths of interest. So there is, of course, the good path, and there is the loop. Sorry. Okay? What is nice with those two paths is that this part is in common, this part is in common, the difference is just there. So if really it thinks here and not here, it means that in this period, and remember what we said at the beginning about coding neurons, it means that in this part of the maze, there should be a difference in firing rate before turning right or left, because here, he already knows where he has to go, right? Whereas here, if he doesn't know yet where he has to go, there shouldn't be any firing rate coding neuron. So it's not that perfect. But if you look at the CDF of the firing rate coding neurons, you know, the p-value that I told you about, you see that the red curve is the one showing that there is a lot of coding here, whereas the black curve, which is still above the diagonal, but it's less above the diagonal, is the coding here. So there is much more coding neuron here than here, which corresponds to what we showed on the behavior. Okay, so we were happy with that. But of course, it would be super nice to do that with networks. Except that here in this experiment, this part is too small to really do network decoding as we did, because we don't have enough spike to do the interaction function. So we don't know how to do that. We should have another experiment with longer trajectories, and that's why the maze now they are doing is much bigger than before, because we need longer trajectories to be able to do this kind of reasoning on the network.
How many neurons do you have?
So the that you need the rat to do exactly those two paths. So if you do the Benjamin-Hirschberg stuff, you end up with here, for instance, I don't remember why you have two lines, but here you have, for instance, 15 coding neurons over a total number of neurons, which is 62. Whereas here, so in the ones that descend, you have only 2 coding neurons. So you have much less here than here. But, okay. There are other behavioral questions we can answer. And I don't want to go into details, but if you are interested, I would be happy to tell you. For instance, you can use Cox model and survival theory to understand what is the order that makes you learn the quickest. Because when you learn, of course, you have a certain, you have to learn until you reach a certain percentage of success. And depending on the order in which you have been given the object, so remember that's all again in Julia's experiment, you're going to have more or less easy order that is making you just give up or have a very long learning time. And for instance, what is the worst is if we we shuffle the object all the time. So even if they are given in a kind of logical way, each time you have a new bunch of objects that is not exactly in the same order as before. And if we do that, people don't understand anything and they spend 40 minutes trying to guess, and like 10 to 20% of them just give up. Okay? So you can show statistically that this is what's going on. Another thing that we can detect, it's with another model that cannot be explained with this kind of model, but we see it on data, is that you have eureka moments when you learn. Which means that at one point, you pass from a very low performance to a very high performance. And this moment depends on the person. There is no way you can align segmentation to do that. So you have to guess where is your eureka moment, individual per individual. And then when you align them, you realize that once you have a good estimation of this eureka moment, you have a switch in performance that none of this theoretical model would explain. Exactly. Okay. One last stuff, because I hope in October we will have an online experiment for adults and kids where we learn the rockets that are landing on the moon, just to make it fun for kids. But it's exactly the same protocol as for the objects. You have two categories, the rockets that land on the moon, the rockets that don't land on the moon. And again, we will record reaction time to see if we have a more complex model that includes reaction time. And for this reaction time, what we would like to fit is what Sophie is doing into PhD thesis, which is a real neural network like a Hawkes process with a learning rule. And we would react when we see a statistical difference of firing rate between the different outputs of the different neurons that are coding for each category. So that's exactly what she's doing in PhD thesis. And so I just wanted to make some advertisement for this experiment, because if you want some fun, it should be ready in October. And so as a conclusion for the learning data, okay, handling learning data is super difficult from a statistical point of view, even if we are just looking at behavior, without even thinking to match it with neuronal data. Julien Aubert, which is another PhD student of mine, is trying to justify the cross-validation that I told you about. He already justifies the MLE part when the learning rate is slow. And the main point is that the link between the cognition, which is the learning process, and the neuronal substrate, meaning what's going on inside the neuronal network, is far from clear. What we have shown with our network coding strategy is that we can catch somehow a part of the genetic trace, meaning we know more or less which region is coding what and with which proportion during the different stages of learning. But we cannot track the data in all the brain, so we don't know exactly where they move. For instance, right now, I have another student working with hippocampus and prefrontal cortex, and we have just those two regions. And at one point in the experiment, when it's very late in the learning, well, none of the regions seems to code, and probably the code is hidden in the striatum, but we don't have the data at the same time because they cannot put electrodes everywhere. So it's hard to track. Also, we cannot track the network day after day because I told you, for instance, there is cicatrization, so you're losing neurons. Then you can move the electrodes, so you are switching regions, etc., etc. So day after day, you are not recording the same network. That's why we went to the decoding power to have a kind of measure that will be there for all days and we can compare. But then we are trying to do it from another point of view, which is what Sophie is doing, which is, okay, let's build mathematically a Hawkes network that learns, and then we will fit to the behavioral data what the neuronal networks predict, and we will see if it works. So that's our PhD thesis, and I just want to thank her a lot for all the exercises during the week, because it was a lot of work. And okay, that's it. I was very happy to give you this course. And that's the reference. Yes.
When you simulate your model, don't you?
This one?
Yeah.
Yeah.
You don't see any kind of this kind of shot.
No. No.
We can see one.
No, there is no. At least on the simulation we did, yeah. We tried, but no.
Even in a single product.
Yeah. What? No, these models, they don't have a RECA. It's kind of smooth. And Sophie's network, the way it's programmed, is also kind of smooth. But again, the complexity of your brain is amazing. There is eureka moments on people. So, yeah.
Will there be a difference between this brain learning and cerebellum learning?
Yeah.
Because that's more brain.
I don't know. I never had data on cerebellum yet. So because my knowledge of what the different parts of the brain are doing, I'm not a biologist, so I learn them when I have data. So I don't know exactly what the cerebellum is doing.
Cerebellum is like emotional equilibrium.
Yeah.
It learns to speak.
Yeah, okay.
No
But I think the data in the cerebellum, they are easy to get. I'm not sure. Yes, it's hidden, right? It's very deep. So the only data I have seen on cerebellum usually is that they put it out and they put it on slice. So you're far from having learning data. I don't know. Maybe there are some people who are able to record there. I don't know. So I don't know exactly the role of the cerebellum in all that. Oh, yeah.
The equation you wrote for this for
Yes.
the equation you wrote for the probabilities in what small. Do they also for models with reset?
This one?
Yes.
Yes.
For Galves law.
You have this?
No.
Ah, I don't know. I don't know to make the computation for. Maybe you could. You have to make the equation and see what it means. I really don't know. What is well, but in fact, Galves and Loscherbach, they are also linear. I mean, if we are looking at the linear stuff, the computation here was super easy because you see this thing is linear in mu and g, so you can derive, and it's quadratic and. Okay, it's easy to find what is the formula, and that's why you get this covariance formula. If it's not linear, I don't know. So even a Hawkes process that it's not linear, I don't know. What's changed exactly when you stop it at the last spiking time? I have no idea. Maybe the formula that you get out is not just a covariance, it's something more complicated, which would look like your events. You see, like G has just spike, and then what is like a triple of covariance. Well, it's not really a covariance, like 3 stuff. Maybe that's what's going on. I have no idea. Yeah.
And is the data from the heart strain available?
Not yet, but they would be. Once we have published everything, I pushed Ingrid to release them. What is already public is the one we have played yesterday, which is just 1 rat, 1 day. And also I didn't give you all the... because there is a lot of pre-processing due to the fact that you don't have the path, you have the a video of the rat in the maze, right? So you have to clean the data to know which path is what. So I don't know how we will release it. So I cut it for you for the exercises. I don't know if I would release the cut data, like you know where you are and which path is taken, or if we make like the whole thing available.
Maybe we could convince Ingrid if you tell her that we have data from EEG and not a learning task, which is a goalkeeper.
Yeah, I know.
We could exchange.
No, but I think she's ready to put them online because most of the data on the rats, they are 10 years old. We had to put more rats, but most of the rats were recording 10 years ago, and it took them that time, you see, to also collaborate with mathematicians to exploit what is inside, because they were so complex that it was very hard for them to understand what was going on. So now we published, well, the paper on learning is published. The paper on really the coding of the network, it has been submitted. Once all of that is done, maybe I can convince her to.
So, you know, in literature, people got data and they use it for 40 years.
Yeah.
And then made the DVD. So,
Yeah, so that's what I'm saying. Yeah.
okay, but you could maybe use this. We have a data on EEG
Okay, yes.
for very interesting learning task, which is a goalkeeper game. I could try to convince my partners to exchange.
Yeah, great. But I think learning data with EEG, it's even messier than learning data with spike trains.
factorization in EEG, you don't have.
Yeah, that's true. This part you don't have. Yeah, that's true. It's just that they are so complex. I mean,
Yes, but you find things.
Yeah.
You find context clues,
yeah.
which was not obvious. No, okay, but
Yeah.
I think it would be interesting if the data become.
Totally agree.
It was a great study of lessons. Thank you very
Thank
much.
you.
those things are important is and probabilities question and I want to introduce him because he's very important in my life. I like him a lot. So thank you for everything and to be here, and this is an opportunity to learn more beautiful things. You can show us. Thank you. And you, Pierre. Pierre, please.
Thank you. First, I would like to say a few words about Antonio. 4 or 5 months ago, we just concluded that we've been knowing each other for more than 40 years. And for me, that was a very nice friendship. We had a lot of scientific cooperation discussions, but we also shared many things intellectually and otherwise, and together with Charlotte, of course. I know many things from Antonio, and I always admired his energy and obstination when he developed and managed so many fruitful and important enterprises. As I said, it was for me a marvelous friendship, and I hope it will continue for many years on. Thank you, Antonio. So now let me go to the talk. Let's see. Here. Okay. So this is a joint work with Jean-René Chazot, and part of it with Serret Martinez. There will be 3 parts. The problem, and then speak about the notion of resilience and some recent results about spectral gap. So the ecological dynamics is developed by ecologists as different system of differential equations acting on the concentration of species. So you imagine a system like that. And very often, the system has a built-in splitting, so the vector field is split into the difference of 2 vector fields, where the first vector field B is a burst flux field, and dLx is a depth flux field. And both have non-negative components, and they vanish at 0. Vanishing at 0 is very important because it reflects the fact that there is absence of spontaneous generation. So the splitting, of course, is far from unique, but it's coming usually from biological intuition or experience of the model. I mean, the origin of this model is the interaction between individuals, which is quite reminiscent of clinical situation. Not much is known about the expression of this interaction of these quantities B and D's. And so it's a kind of choice of the modeler to decide which B and D to use. But the general setting is the one I described. There is a vector field system of ordinary differential equations, and the vector field is given by the differential fields, which have interpretation in terms of burst and depth. So what I will consider in this talk is situation where the number of individuals is very large. Now, in the previous setting, I was only speaking of concentration. No individual, just the concentration of individual of each type of species. Now, there is usually a parameter in the system which is very large. I will call it K. But you have to be careful about one thing. This parameter is an order of magnitude of the number of individuals that can be maintained as the resources. It's not an explicit parameter. It's a scale. So in particular, it will never be observable. All formulas at the end, they will get rid of this parameter K. So it is proportional to something which ecologists call the carrying capacity, which is the size of sustainable population in the system. And I said it's not observable, but it will give a scale of the number of individuals present in the system, and the relation between the concentration and the number of individuals is simply this relation xj equal nj over k. Now, of course, you can change k by 2. I told you it's a scale. So in this case, I tell you count. Nj is what it is. So in this case, xj will change by a factor 2, but it's this kind of rescaling. It just doesn't matter for the dynamical system. It matters for quantitative results, but not for qualitative results. So the real-time evolution will be constructed from birth and death trace of an individual, and each PC will describe the bioecological interaction. For example, models are built with sexual or asexual reproduction for birth, competition, and other mechanical for death, etc. There's a lot of systems of that form. And okay, so let me go to the probabilistic approach. So what we did is from the macroscopic birth and death rates, you can construct microscopic birth and death rates using this parametric K. And this goes like this way. If you have NJ, individuals in the of the species number Q, then the rate at which the species number J increases, so there is birth, is given by this quantity. So K, B times J, there is a rescaling of the total population and the usual factor G. So these are the infinitesimal translation rate for birth. There is an infinitesimal translation probability of transition for death, and there is of course 1 minus the total for nothing to. Now, for example, if you the simplest case would be a linear birth rates, and in this case, of course, the probability there is a dt missing here. The probability transition is just proportional to the population. So then in that case, lambda j is the birth rate of each individual of species j, and lambda j n j would be the birth rate of the total population. Okay. So as I said, we require that vanishing to avoid spontaneous generation. Now, in fact, my talk will be organized around several time scales, and that was the motivation that we had at the beginning. We wanted to understand how all these time scales are related. The first time scale you encounter is a time scale at which something happened in the population. Some individual give birth, another dies, and so on. And the time scale of these events is 1 over k, because there is a k in front of the dt here. So the time scale of something happening in the population is 1 over k. So this is a very short time scale. You should imagine k to be large. Typically in bacterial population, k times can be a million or a billion or something like that. So it's really very large. So this time scale is very short. Now, from these transition rates, you can construct the generator of the associated Markov process. So here I just wrote the generator for one species. So there is a birth with a decreasing of the number of individuals by 1. There is death with a decrease of the number of individuals by 1. Of course, if there is nobody, you cannot give birth, and if there is nobody, you cannot die either. So if you look at this particular generator, for example, this process has only one periodic invariant measure, which is a Dirac measure at 0. So ultimately, the whole population will disappear. But of course, we've been interested in describing the statistic of the system for various time scale, eventually avoiding this ultimate catastrophe. So you can write the Fokker-Planck equation, you can skip that. Now, for a time scale of order 1, so remember the population time scale is 1 over k, but for a time scale of order 1, you have convergence. When you take k, let k go to infinity, you have convergence of the process to the vector field. So that's a well-known result of Crux, which is that if the initial condition scales correctly, then at time the initial condition scales correctly, the time t, the whole population will also scale correctly with k, and the limit is the solution of the ordinary differential equation with this initial. So we get back to the initial dynamical system. Now, larger time scales, so time scale much larger than 1, things can be very different. For example, when you are on a time scale of order log k, the trajectory stay close to a diffusion process, which is driven by the vector field and as the diffusion coefficient, which is proportional to 1 over square root k. So there are, this is sort of standard scale, but the thing which is noticeable is that here we're not at equilibrium. It can be any point in the phase space. So there are recently results hold on extended results of course in this direction, where you have in some sense the first stochastic correction to the quartz result. The quartz result would be simply this, then here you have a stochastic correction. But we are even interested in much larger time scales. For example, infinite time scales. Now, the first thing I have to do is to introduce a notion into the hypothesis of descent from infinity. That's quite natural in ecology. If the population is too large, death will dominate birth. Because, for example, there is not enough food for everybody, so many individuals will starve to death. So, under the hypothesis, which I'm not going to make very precise, but I think you can understand very simply, the process reaches 0, so the whole population completely disappears almost through infinite time. So this would, even if the fixed point is repulsive, that's a bit different from dynamical system. Usually in dynamical system theory, when you have a repulsive fixed point, you just ignore it. That's not very interesting. Here, you always, almost surely end in this repulsive fixed point where everybody is dying. And so that's what I say. And the vector field, if you start out from the origin, you will never reach the origin if it is unstable. So the natural question is to ask how big is this T0? How long the whole system will survive until this catastrophic event will occur. So there are a few hypotheses that we introduce, which are quite natural in ecological systems. So we assume that the origin is a repair, and that there is a unique stable fixed point of the vector field inside the positive quadrant. So the vector field is considered only in positive quadrant because the concentration are of course positive or 0. And we assume that this vector field is stable, is in fact globally attracting except for 0. So this is a rather simple dynamical system, but it's a frequent situation in ecology. And in that case, it turns out that the time of the catastrophic disaster is exponential k. So imagine if k is a bit large, this is a huge number. So you have the three time scales. And 1 over k is the one from the evolution of the population, time scale of order 1, which is the time scale of the vector field, and then this huge time scale where the world disappears in a sense. Now, before I make this statement a bit more precise, let me show you a simulation which was done with only one species, and k over 100. So this is pretty small for ecological situations, but numerically it would be harder to go beyond, much beyond. So there are 4 cases which I considered. Let me start with the one here in the top left. So here I started with the number of individuals which is over 100. So I have k is over 100, and I start with the number of individuals which is over k. So what you see is that the number of individuals as a function of time just moves a little bit erratically, but doesn't vary very much from this number 100. If you start from 50 individuals, the process grows until you reach this kind of pseudo-stationary behavior. If you start from 150, it's again the same thing, goes down to about 100. Now, the 4th simulation is very, very different. Both cases are extremely different. So here I started with 2 individuals instead of over 100. So k is the same, but the number of individual is just 2. And what you see is that after a very small time of order 1 in the normal time scale, the whole population has disappeared. So what's happening is that if you start with 2 individuals, which is small with respect to the k, you have a macroscopic probability to disappear in finite time. But you have also a macroscopic probability to do exactly the same. To do exactly the same as here. So there is about probably 1/2 that you die in before time 1, say, and then there is probability about 1/2 that you reach about 100 and stay there for a very, very long time. So this is a bit surprising that the process stays here, where I said before that it will reach extinction in finite time. So I cannot show you a very long simulation of this, because the catastrophe would happen at a very, very long time. E to the 100 is already a very large number. So, but I can sketch the trajectories, and they look like this. So they wander about 100, and from time to time the population goes down, it recovers, goes down, it recovers, and finally at time of about e to the 100, the whole thing disappears. So it's a kind of pseudo-stationary state which persists for a long time. It's quite similar to a metastability. And in fact, there is a notion which is used to describe this kind of thing, which is the notion of quasi-stationary distribution. So this distribution of probability measure is quasi-stationary, is starting from this probability distribution, condition that you have survived up to time t, you get the same distribution. So if it were not from this conditioning, this would be just a notion of invariant measure. But we cannot, I told you, the only invariant measure is a Dirac measure at the origin, because ultimately the whole population will completely disappear. So to see something, you have to condition to the fact that you have not disappeared up to time t, and then this leads to this definition of quasi-stationary distribution. So this takes care. This is a nice notion when you have a leaking from the phase space. Well, so in fact, for Bersender's process, it's even known that the time, if you look at the time of extinction in the quasi-stationary distribution, it is exactly exponentially distributed. So that's quite reminiscent of metastability. But here it's an exact, it's not an exponent, it's not an approximation. I'll give it okay, so we're not really interested in this large time, because as I said, it's very huge, and so usually you don't see it in behavioral systems. What we're interested in the behavioral system is sort of metastable sense, since it's not so long. So the first question is how to find this QSD. Well, the first step is essentially to write down the eigenvalue equation. That's useful, but usually it's not really useful. That's useful to get properties of the quasi-stationary distribution. Not so often you can get existence from this property. There may exist several quasi-stationary distributions, but in our case there is only one. As I said, describe the quasi-stationary distribution describes the statistical properties of the system for a large time. And in our case, this time is 1 over this eigenvalue, and this is very large. This is exponential decay. And in dimension 1, we are very precise. I mean, I can tell you exactly what is this over 1 in dimension 1 in terms of the birth and death rates. And in fact, you have also a notion of convergence to a rate of convergence to this quasi-stationary distribution. If you start from a given initial point, and in fact, the bound, this is a bound. So the proof that we used is was already, there is a general proof by condition for existence of quasi-stationary distribution by Champagne and Vimonet, and we use their proof and put the k and everything there, and it emerges this rate of convergence to the quasi-stationary distribution with a time scale of order log k. So that's another time scale. So here we have the 4 time scale, 1 over k for the population, 1 for the vector field, log k for the convergence, and the time of the catastrophe. I will come back later on at the end of my talk to this log k, which was a bit surprising to us. So let me show you a few properties of this quasi-stationary distribution. It has exponential moments. The average is, of course, proportional to the escape times the fixed point of the vector field. So that's really the carrying capacity. So that's what we call it. It's called the carrying capacity. That's the number of individuals present in the system at the pseudo equilibrium. Certain moments exist. There's a lowdown on the variance. The variance is about the k, but we have also a lower bound. And there is a Gaussian approximation near the average. It's a kind of central limit theorem, but the proof is rather different from the standard proofs of the central limit theorem. It's not a central limit theorem in the sense that we have a sum of dependent variables. Now, let me skip that. I will not choose it later on. I mean, the semi-group is well defined as a minus order. Now, the question we ask is, all this is a sort of theory. You start with given birth and death rates, you introduce the k, you prove theorems and so on. But what can you do from this if someone comes to you with data? Unfortunately, data are very rare in ecology, or at least serious and long enough data. There were some for this kind of problem. I'm afraid they're lost. But we hope that there will be many more in the future. So the question is this: assume we have only one, and when you get data, for example, someone with a lot of patients measuring the number of bacteria in a pond for 1 year for various types of bacteria. With one realization of the process. So it's a recording of these vectors as a function of time. Now, as I said, we cannot repeat the measurement. We can split this time interval in several species, but that's the only thing we can do to repeat the measurement. We cannot go back to the pond again and do it. That's excluded by the possibilities of the graphs. Now, we neglected in the analysis some more measurement problems like measurement error, discretization, and so on. So we assume we have this and that. Now, we don't know the vector field, we don't know the birth rates, we don't know the death rates, we don't know K, and we know very few. We assume we know the number of observed species because that's the size of the vector n of K. And we assume that there are no other unobserved species, which is an assumption. Now, from this, we would like to have information of the birth, death, and so on, and another quantity that I will introduce now. But how can we get this information for the data? And what are the good questions? What are the questions of interest to the ecologists? Well, of course, we can estimate the fixed point of the vector field by standard technique, and accuracy is the standard one over script K. You just do averages over time of these quantities, these vectors. Okay, so from the previous result that I showed you, in particular the simulation, you see that if T is not too large, the system will wander around the fixed point, around K star. And then if you look at the ends, they will wander around K star. If you look at the concentration, they will randomly wander around the fixed point. So the information we can get about these quantities, V, D, and so on, there will be only information around the fixed point. Okay. So how do you do that? Well, there's one quantity which ecologists love a lot, which is called the resilience. So let me explain to you what it is on the vector field. So this is related to the stability of the fixed point. When you, in dynamical system theory, to look at the linear stability of the fixed point, you take the differential of the vector field at the fixed point, and this is the matrix, and the spectrum of this matrix tells you about the stability of the fixed point. Is the spectrum in the left hand plane, the spectrum, the fixed point is stable. If it's in the right hand plane, it isn't stable. So this is called the engineering resilience. And the engineering resilience is defined as the real part of the eigenvalue which is nearest to the imaginary axis. So this is this will, in a sense, control the rate of convergence to the fixed. There is another quantity, but which is much harder to detect, which is called the ecological resilience, which is the size of the basin of attraction. It's more difficult to quantify because to reach this quantity from the data, you will have to wait for large deviations. And of course, large deviations take a very long time. So nobody has the patience to look for that. So usually you look for the engineering resilience, and to look for this engineering resilience, you have to put your hands on this matrix. So engineering resilience is useful for at least two major purposes. It gives the exponential rate of relaxation to the equilibrium after a small perturbation. So if you have perturbed the system, it will recover, goes back to X star, and the time it takes is the inverse of this. The time scale of this effect is the inverse of this quantity. It also gives you an estimation of the change of equilibrium after small perturbation of the system. This is connected to the implicit functions. I will not say more. So, question is how to determine the engineering resilience. Now, there is a way to do that, which is to kick the system in different direction and observe how it returns to equilibrium. But this is difficult to perform experimentally and not very ecological. So, can one measure the resilience just by observing and recording the time evolution of the system? Remember, having only this trajectory. And the first thing we did was to prove that there is an Einstein relation. So if you look, so this is the matrix of the differential of the vector field at the fixed point. This matrix is the diagonal matrix of the birth and death process. At the equilibrium, the birth and death processes are equal. The system, they just compensate. And sigma is a covariance matrix of in the quasi-stationary distribution. So this sigma is about the k, this d is about the k, and this matrix is about the 1, the 2 is about the 1, of course. So all this is about the 1, and you can prove that the error is about the square root k. So if you knew one, so sigma you can observe from the data. D you can also observe from the data. You just wait until somebody gives birth and somebody dies and so on. So in principle you can observe sigma and D. And so the question is, from this equation, can you reconstruct M? So this is called an Einstein relation because it's the equivalent of the famous result of Einstein in 1905 when he wrote the equation for the friction coefficient. Here it is, which is in which there is for the fluctuation, the size of fluctuation in terms of the friction coefficient, that there is a mass of the system, there's this Boltzmann constant and the temperature. So you have here again, it's sometimes called the fluctuation dissipation theorem. So this is the dissipation, the resilience, the train to go back to the equilibrium, it dissipates. And here you have the fluctuation. And here you have a sort of source which is given by the birth and death effects. So can you solve this equation? This is known as a Sylvester equation. Now in one dimension, it's obvious. I mean, these are not matrices, these are just numbers. So you just solve it and that's it. But in dimension greater than 1, this equation has many solutions. There is only one symmetric solution, but we prove that generally in ecology, this matrix M is not symmetric. So there are many solutions. You can classify them, but the question is which one is a good one? So this is a kind of, so the relation must be satisfied up to order square root k, but doesn't give you the solution of the problem, doesn't give you M. Incidentally, in physics, this is called the matrix of kinetic coefficients. I won't choose that. So, so what we observe is that instead of looking at the static equal time fluctuations, if you look at the dynamical correlations, then you get an equation, because you can prove that the dynamical correlation, so the correlation between the number of individuals at different times, this is given by this quantity. So this, if you multiply the correlation at time tau by the inverse of the correlation at time 0, then this is an exponential of tau times the matrix. So this can be measured. This has been, of course, measured. It's just you just make a lag in your averages, and you measure this quantity. And so these quantities can be estimated from the data. And for example, if you take tau equal 1, you cannot. It's not a good idea to take tau large because then the error will become large. But if you take, for example, tau equal 1, then from the data you can estimate the matrix M, and so the. So the assigned relation, of course, will still be valid, but just sort of confirmation of the quality of your experiment. Okay, so that's for what we can extract from the data. And again, I want to insist on one fact, is that the resilience is a macroscopic quantity. It's related to the vector field. There's no individual share, it's just concentration, and that's it. So it's a macroscopic quantity. And as usual in the fluctuation dissipation, you relate this macroscopic quantity to microscopic fluctuations and to also these microscopic rates. So there is the success of this relation is a relation between microscopic fluctuations and macroscopic quantities, and that's a big discovery of that. So let me come now to the spectral gap. As I mentioned before, the rate of conversion to the quasi-stationary distribution is bounded below by 1 over square root of 1 over log t. So that was what we got from the Champagnat-Vimolet result. We also have the proof for this quantity using Poincaré inequality in dimension 1. And although this is a large separation of time scale, I showed you these time scales. Yeah. And so you have the 4 time scales. This log k is usually not, even if k is very big, if k is a billion, that's not a very big number in any case. But you have certainly a very large separation between these scales, this one, and this one. But we were curious about this log k, which was sort of a bit unnatural. And so we wanted to understand more about it. It is connected to the fact that you have an operator which is a generator of the process. This generator has a discrete spectrum. And what you want to know is the spectral gap of this generator. Now, this is a quantity we estimate is a lower bound of the spectral gap. And so we were wondering if we could get at the truth, that is to say, at the exact value of the spectral gap. Now, up to now, we can only do that for one species, so in one dimension. But and the reason is that we can put the problem in a self-adjoint framework, which helps a lot in this kind of analysis. But I told you that the spectrum is discrete, and the spectrum is negative. It consists of simple negative eigenvalues, so there is no degeneracy. And I told you that the dominant eigenvalue, the lambda 0, is very small, it's very near to 0. There is a minus sign missing here. So it's minus e to the minus k, essentially. So the k is big large, it is a number which is very, very near to 0. And we have this estimate that the lambda 1 is smaller than 1 over log k. K is a bit large, of course, this is not, this is a small number, right? So we suspect that this is not a very good estimate. So can we do better on the spectral gap? So the spectral gap is the difference between lambda 0 and lambda 1. This is the quantity which tells you at which rate you convert to the quasi-stationary distribution. So the inverse is the time scale of convergence to the quasi-stationary. You can ask even more. You can ask, is there a limit for the spectrum as k goes to infinity? So recall that in one dimension, the vector field is pretty simple. It's just the equation, the dynamical system is the x over dt d of x minus d of x. And let me recall the hypothesis. So d of 0 is equal to d of 0 equal to 0. D prime of 0 is smaller than b prime of 0 because 0 is an unstable fixed point. And this is a condition for the fixed point, and the fixed point is stable, so d prime of x star is smaller than d prime of x. And there is no further fixed point. The limit of d of x over d of x at infinity is 0. That's descent from infinity, the fact that if the population is too large, many will die, and there is some technical assumptions which are not very important in this case. Now, let me define two arithmetic subsets. The first one is b prime minus d prime. So remember, this is a negative quantity times the set of all positive numbers, 0 included. The second set is d prime of 0 minus d prime of 0, and this is again negative, times only the positive integers. And the theorem is the following. The limit of the spectrum is the union of these two arithmetic sequences. But you have to consider them with multiplicity. I will explain this a bit more detail in a minute. And so you just take the union of these two arithmetic sequences. There is 0 here, because here you have 0, but all the other terms are strictly negative, and the spectrum is a union of these two quantities. In particular, for the spectral gap, you get this result. So the spectral gap is in fact of order 1, something that we were expecting. And while the estimate we have gives us a spectral gap of order 1 over log k, which goes to 0 when k goes to infinity. So there is this effect that the estimates we get, in a sense, they are estimates of the time at which a certain operator is of less than 1. But since these operators are usually not self-adjoint, it doesn't give you very good information about the truth of the spectrum. So let me show you a numerical simulation. So on the left, there is a non-degenerate situation. The birth rate is linear, and in the number of individuals, so B of n is proportional to n, and the death rate is cubic. There is an n cube, eventually n squared n. And what you have is, what I do here is minus the spectrum, because the spectrum is negative, so it's better to see positive quantities. For the various, various eigenvalues, so the first 7 eigenvalues as a function of k. So the scaling k is logarithmic, so that things converge a bit more rapidly. So what you see is that these eigenvalues seem to converge, and the stars are the numbers that from this union. So they converge, and they indeed converge to the limit of R. They converge. At k equal to 10 to the 4, they are very near to the limit. Now, here is a logistic case, which is more amusing in some sense. The birth rate is still linear, but the death rate is only quadratic. And you can prove that this case is completely degenerate. So if you look at this series, these two quantities are equal for the logistic case. So your union here, but I said you have to take the union with multiplicity. So there is a 0, which is not here, so it will be stay alone. And then all other numbers will appear twice in this special union. And this is what you see, that at any finite k, even very large, all the eigenvalues are simple, so they are all separate. But when k grows, they converge one to the other, and then in the limit, they coalesce to the values which are put here with stars. So this is an extreme situation of a degenerate, but it's only degenerate in the limit. At any finite k, the spectrum is simple, the eigenvalues are simple and non-degenerate. So there is a fact which is very surprising in this result, which is that the unstable fixed point comes into play. So I told you most of the time, the process wanders around the fixed point. So in the beginning, we were expecting seeing only information about the fixed point, so these numbers. But in fact, for the spectrum, the unstable fixed point are almost never there unless you reach this catastrophic event. This quantity occurs in the spectrum, and it can even dominate the spectrum. For example, if this quantity is smaller than the resilience, you will see that the spectral gap is smaller than the resilience. This is not so surprising because I showed you the resilience is connected to the decay of correlations. Here it is. The resilience and the correlations are spatial observables. Spatial observables here. It's not the complete spectrum. You cannot expect to get the complete spectrum from this quantity. And in fact, you see here that there are cases where the resilience is bigger than the spectral gap. Another well, I told you already this about the merging of the eigenvalues at infinity, but not at time. Okay. So the proof of this result of this theorem that the limit of the spectrum is rather long. I will just give you a very brief sketch of how it goes, just to give you an idea. The main idea is that you split the problem into three pieces. There is a piece near n equal 1, another piece near the fixed point or n equal kx star, and then there is the rest. So n's which are not near 1 and which are not near 2. What you show is that the rest have not contribute, and that's one of the main issues. And that's an issue that we don't know how to tackle in higher dimension for several species, so in higher dimension. Now, around X star, what you do is, you've seen that in X star, I showed you that there are normal fluctuations. That was in the properties of the system. So here I showed you that near the average, near Kx star, the fluctuation, your normal fluctuations, the variance is over the k and so on and so forth. So you imagine that the right scale is square root k. And so you rescale by square root k near, you rescale by square root k near kx star, and you take the limit k to infinity, and you discover that what you get for the generator in this area is a harmonic oscillator. The spectrum of the harmonic oscillator is well known, and this is an arithmetic sequence, and that's this first sequence. So this one is not very surprising, and we were expecting it for a long time. But the other one is more surprising. So for n near 1, not that much to do, then keeping only the part which is linear in n in the generator. N is small, so the other factors, they have a 1 over k in front, so you drop them. And then you get this very simple operator. So it's just a burst and this process with linear burst and linear bits. But n is not very large. Now, what you easily find is that there is an arithmetic sequence of eigenvalues, which are exactly these guys. And the eigenvectors are the discrete orthogonal polynomials for the discrete measure given by these weights. So that's an explicit computation. You fiddle a bit around and you easily find that. The question is, you have a sequence of eigenvalues, you have the corresponding eigenvectors. Is it the whole spectrum? You have to prove something that there is no spurious eigenvectors, spurious eigenvalues, which are not of the form of these arithmetic sequences. And the key is a theorem by Percy Deicht, which says that the spectrum is complete because the Hamburger-Stieltjes moment problem for this measure is determinate. So this means that if you look at the moment of this measure, this is a sequence of numbers, and there is only one probability measure which has this sequence of numbers at the moment, and it is this one. And the theorem Percy said, in that case, the spectrum is complete. This is not a probabilistic argument. It uses complex analysis and so on. It's quite a delicate result. So this is how we prove that. The spectrum for this operator is exactly this sequence of numbers and no more. And so the spectrum, in the limit, the spectrum is given by this unit. Okay, so thank you for your attention and my congratulations and thanks to Antonio.
Antonio first.
No.
Hi, Pierre and Roberto. Can you hear me?
Maybe you cannot hear me.
Hi, I'm Roberto. How are you doing? Can you hear me?
Yeah.
Hear me?
Yes.
Okay, so my question is, can you interpret this result as kind of a typical evolution in metastability, that the system will stay around this X star for a while, and every small fluctuation will bring it back very quickly, unless you have the large fluctuation that takes you to zero. Is that the...
Yes. This is exactly, can you see that? This is exactly the sketch. You stay near, forget this for a moment. You stay near the pseudo equilibrium, and then, boom, the thing disappears. Now, the thing which is a bit more complicated than usual is, well, usually it's always like that also. You have in between, you have attempts. There are also attempts to go higher, but it's more difficult to go up than to go down because if you go up, the base rates become very large and so on. But there are these attempts, I mean, and at the end, there is an attempt which is successful, and then everybody is dead. So you cannot recover from this. That's a bit different from usual metastability. Or usually here, if you wait very, very long again, you can go back here.
Don't say this to Roberto. Roberto does not agree. You say that this is not metastability, it's stability.
Not totally. So, metastability will be that the final end will be to equilibrium, which for you is zero, but the other one will be the equilibrium measure. But in the intermediate end, this is typical of metastability. When you get very out from the well and you stay midway, you come back quickly instead of, you need to have a full excursion all the way out to really reach equilibrium, which for you is reaching zero.
Exactly.
Okay, thank you.
I have a question there. So, avoiding all theological discussion about the difference between tunneling and metastability, I'd like to ask you something about resilience. I was not aware of this notion. So, we listen a lot about a system is resilient, but I never knew how to define it. So, you know that you have metastability or tunneling in systems, in biological, neurobiological systems, or in...
I'm sorry, I don't hear you very well, Antonio.
Okay, let me approach. So,
Yeah.
so I'm asking you something about, can you hear me now?
Yeah, that's right.
About the notion of resilience. I did not know about this definition. So, so you... No, the question is the following.
It should be good.
Huh?
I think you can talk.
I don't know if this really. No, you can measure resilience this way. So, what this tells us about the system? Because you can have resilience in neurobiological systems, you can have you have metastability in neurobiological systems, in social network systems, you can prove it. Really, and you can observe it. So maybe we could look at this resilience properties. I think the resilience of thing like the average size of the fluctuation before the final fluctuation. Is that correct? Yeah.
I'm sorry?
Can you define resilience as the average size of the fluctuation before the final one?
No, because you see in this graph, there are peaks everywhere. You know,
Yes.
can you see this graph?
Yes.
I drew a few of them, there are peaks everywhere. It's simply there are peaks here, going down. But they miss the zero. It's only this one which is.
Yes, that's precisely what I asked. Precisely what I asked you. Can you define resilience as the average size of the fluctuations, given that they are not the final fluctuations?
Oh, what do you mean by the average time of fluctuations?
Well, you look at the fluctuations, at the difference between the average plus stable
Yes,
position
yes.
and
Well,
like,
that's a conjecture. So what you do is, for example, in this graph, you take n equals 60. You start here, and you ask for the first time you reach 60. And you ask for the second time reach 60 and so on. Now, this would probably be very near to a Poisson process.
yes, yes.
Maybe you have to take more, you have to take this 100 to the infinity to get the theorem in the limit. But I'm sure there is a lot of Poisson process and exponential distributions even in that thing. The ultimate one we know because this is the Fourier stationary distribution, and so we know this is exponential. But in between, there are probably very, very many. But that should be the same thing in the standard metastability situation. If you ask, for the first time you reach half of the well, don't have to go to the top of the well, to go to the other side, but ask to reach the half of the well. Then you can record the 60 times, and then probably in the limit form a Poisson process when you are adequately risky.
And this reminds me think we did it together when you look at turbulence systems and the
Yeah.
loss of turbulence. Okay, thank you very much. It was very interesting.
You're very welcome. Now, there's one thing I want to say here about quasi-stationary distribution that I forget. This is a situation where you see the quasi-stationary distribution because K is large. Usually, the thing just goes down very fast and you don't see the stationary distribution. That's also, you see, you have to do something, and here to see the metastable situation, you have to use this large parameter. Otherwise, if you take K small, there is nothing, you don't see anything. The system dies and that's it.
Any more questions?
Thank you for your talk. My question, could you
You're
give
welcome.
us a reference for this, how to estimate this resilience from finite time correlation? As you mentioned, there is a relation, right? And you can estimate from.
Yeah, I had the slide on that because we did, in fact, yes, so we did a lot of statistics about these quantities. So this is how you estimate the different objects. So this is to estimate the fixed point. This is to estimate equal time correlation. This is to estimate the birth or death rates, and this estimate the time correlations. And then we computed in our paper, because we have so much information about the system, we could compute the rate of convergence of these statistics. So in fact, we can estimate, for example, for this one, how long do you need what's the length of the recording you need to have a good approximation for this quantity and so on. And I don't show you the other one because the formulas are more complicated, but there are formulas to estimate the rate of convergence of these statistics to the true value. Was that your question, or?
No, but you have a reference for where
it's in our second, it's in our third paper.
Okay.
It's in this paper.
Thank you. I will copy the reference. Please leave it there for a while.
Yeah.
Let's thank Pierre again.